Hi, in this video we'll look at different examples where limits are evaluated using Hopital's rule. In the first example, we use Hopital's rule more than once to evaluate the limit. In the second example, we see another type of indeterminate form where it is possible to use Hopital's rule. In this first example, we want to evaluate the limit as x approaches infinity of x squared plus x plus 1 over x plus e to the x. Before doing anything, we must see what is the form of the limit. When x goes to infinity, x squared, x, and e to the x go to infinity. Therefore, both the numerator and the denominator go to infinity, and this is the limit of the form infinity over infinity. And we know that we can apply Hopital's rule. Taking the ratio of the derivative of the numerator and the derivative of the denominator, we get the limit of 2x plus 1 over 1 plus e to the x. So that's by applying Hopital's rule. So once again, we get a limit of the form infinity over infinity, because 2x plus 1 does go to infinity, and so does 1 plus e to the x. Now, a common mistake would be to conclude at this point that the limit is 1, treating infinity as a number, but that would be wrong. Instead, we can apply Hopital's rule once again. We get the limit of 2 plus 0 over 0 plus e to the x, which simplifies to 2 over e to the x. Now, this is the limit of the form 2 over infinity. And this is not an indeterminate form. Dividing 2 by increasingly large numbers will give numbers that are getting closer and closer to 0, and therefore the limit is 0. Now we discuss other types of limits. So now when we have a limit of f of x times g of x as x approaches a, and it is of the form infinity times 0, we can do the following. We can send g of x in the denominator and rewrite the entire expression as the limit of f of x over 1 divided by g of x. Now f of x still goes to infinity, but 1 over g of x goes to infinity as well now, since dividing 1 by a quantity that approaches 0 will yield a quantity that goes to infinity. Could also go to minus infinity. So we now have a limit of the form infinity over infinity, and we can apply Hopital's rule. The other option is to send f of x in the denominator and rewrite f of x times g of x as g of x over 1 divided by f of x. Now g of x goes to 0, and 1 over f of x goes to 0 as well, since 1 over a quantity that goes to infinity yields a quantity that goes to 0. Now the form of the limit is 0 over 0, and Hopital's rule applies once more. So in both cases, we can apply Hopital's rule, but usually only one or the other of the two options will lead to a limit that is simpler than the one we had started with. In this second example, we look at the limit of x squared times ln of x as x approaches 0, coming from the right. Note that it makes sense that we only approach 0 from the right, since ln of x is not defined to the left of 0. As x approaches 0 coming from the right, ln of x, which has a vertical asymptote at x equals 0, goes to minus infinity. Therefore, this is the limit of the form 0 times minus infinity, so the type we had just discussed on the previous slide. We cannot apply directly Hopital's rule, but by sending either x squared or ln of x in the denominator, we will create a limit where we will be able to apply it. Here what works is to send x squared in the denominator. I know because I have evaluated many limits of this type where a polynomial multiplies a logarithm, but knowing which of the two factors to send in the denominator comes with practice. So we get the limit of ln of x over 1 divided by x squared, which we can write as x to the minus 2. So far we've not applied Hopital's rule, but we've just rearranged the expression. If we want to apply it, we need to look at the form of the limit. And here, when x approaches 0 from the right, ln of x approaches minus infinity, and 1 over x squared approaches infinity since we're dividing 1 by numbers that are getting smaller and smaller. So we get a limit of the form minus infinity over infinity. And we can apply Hopital's rule. So doing that, and notice the little h above the equality sign to indicate that I'm applying Hopital's rule, we get the limit of 1 over x divided by minus 2x to the minus 3. So we've divided the numerator and we've divided the denominator and took the ratio. And we can write that as x to the minus 1 over minus 2x to the minus 3. Now simplifying the powers of x gives minus x squared over 2. And as x approaches 0, this approaches 0 over 2, which is just 0. Now let's take a look at what would have happened if we had started our computations instead by sending ln of x in the denominator. Because ln of x goes to minus infinity, then 1 over ln of x goes to 0. And by sending ln of x in the denominator, we get a limit of the form 0 over 0. We write 1 over ln of x as ln of x to the minus 1 to better differentiate it. Now we apply Hopital's rule. And notice again the little h above the equality sign. And that gives a limit of 2x over minus ln of x to the minus 2 times 1 over x. And note that for that last derivative, we have used the chain rule. After simplifying our expression to remove any negative power, we get the limit as x approaches 0 of minus 2x squared ln of x squared. Now, if you compare this to the limit of x squared times ln of x that we had started with, it is very similar, but now ln of x is squared. And this makes the function and the limit even more complicated than what we had started with. So this indicates that we should backtrack. The choice was wrong in picking ln of x and sending it in the denominator. And we should try to send instead x squared in the denominator. And this is what we had done on the previous slide, if you remember. So the moral of the story here is that when we apply Hopital's rule to evaluate a limit, we need to verify that the new limit that we get is at least as simple as the one we had started with. And if not, we can try to see if Hopital's rule can be applied in a different way. So a good example of that is our limits of the form infinity times 0, since we have always two options, depending on whether the first or the second factor is sent in the denominator, as we had illustrated it in the previous example. Or we can always apply other techniques to solve our limits, such as factoring, conjugates, or just simplifying the expression. To conclude, the limit of x squared ln of x as we approach 0 is 0. And note that ln of x is not defined as 0, and so is x squared ln of x. They're both undefined as 0. The reason why ln of x is not defined as 0 is that it has a vertical asymptote there. But our limit indicates that x squared ln of x does not have that feature anymore because the limit exists and it equals to 0. So in fact, the graph of the function x squared ln of x gets close to the point 0, 0, even if it is still undefined as 0. So if you look at the graph, it shows this. Note how the curve approaches the point 0, 0 as x gets close to 0, but that this point is empty since the function is not defined there. Thanks for watching.